opening up the lecture text thread on my phone so that I can see if you ask any questions. Let me know if we're having any technical issues. So last lecture on Monday we were talking about ethers and epoxides, and we explained both of these approaches toward converting an alkene into an epoxide. So the mechanism involving the MCPBA we haven't really talked about since last semester. I'm not going to hold you responsible for that. This alternative reaction to make an epoxide involves the Br2 in the dark, and that's where the pi bond picks up the bromine. It attacks back, electrons leave to produce a Br minus. So that produces the bromonium three-membered ring. Since waters are solvent, it's everywhere in that reaction, it would be the first thing to attack. So you'd have a water here and a Br here. So if you want to get a bromide and an OH adjacent to one another, this would be a good way to do that. Another water would pick off that proton. So really, I should draw it like this, because the Br and the OH are going to be on opposite sides stereochemically, right? Because when the bromine forms a ring, the oxygen has to come in from the opposite side spatially, because that side is already blocked by the Br. So then the second step here involving NaOH, that's used to depronate this oxygen. So the OH minus pick off this proton, these electrons would stay behind. That would be an equilibrium. The OH minus is probably a little bit more stable than the negative charge on this oxygen. Because of sterics, it'd be harder to solvate that and stabilize it through attractions with solvent molecules. But even if the equilibrium only produced a little bit of this, once it forms, before it can pick a proton back up, it might attack there intramolecularly to push out that bromine, which would give you the epoxide. And since the oxygen and bromine are anti-spatially, they're nicely set up for the backside attack that's necessary for the bromine to leave. If the oxygen were on the same side as the bromine, it wouldn't be able to attack, has to attack from the backside. So either of those are perfectly reasonable options for converting an alkene to an epoxide, and depending on what other functional groups might be present in your molecule, maybe one of those sets of reagents, it makes more sense to use than the others. If one set reacts with some other functional group, then it would change the molecule in ways you don't want, and it wouldn't be as controlled of a reaction. So let's take a look at this example, the same thing. I want to use either of these conditions on this reactant. What I expect to get is the epoxide forming, and right now this alkene is flat and there's no chiral center anywhere, so there's no difference spatially between the oxygen from the epoxide coming in on top or from underneath. So there's a nice visual of that over here. And so you can see the epoxide on this flat alkene can come in on top of that, or it could come in from underneath. Either way, what we see though is there's never an opportunity for this bond to rotate. It can't rotate as an alkene, because the p orbitals that exist here have to remain overlapping for the pi bond to remain stable in its form as a pi bond. It can't rotate once the three-membered ring forms because the three-membered ring has locked that into place. And during the transition states, there's really no opportunity for a rotation to occur. So we won't see any rotation there, which is why the methyl groups end up remaining on opposite sides. That's true whether the oxygen adds to the top of the pi bond or the bottom. Spatially, stereochemically, those methyl groups will end up on opposite sides since they began on opposite sides. And the same thing, the isopropyl and the ethyl end up on opposite sides. So what's the relationship between these two? Well, they're a pair of enantiomers. So there's no way to take this structure and flip it around in space like a pancake or rotate any of the bonds and have it lie directly upon the other one. They're not identical. They're not superimposable, but they are mirror images. You could imagine, a mirror here. This one reflecting in the mirror, this is what its reflection would look like. What's farthest away from the mirror is going to appear farthest away in the reflection. This methyl group reflects that one, this methyl group reflects that one, etc. So when molecules are mirror images but not identical, that makes them enantiomers. So another way to draw these exact same two structures, which would probably be more likely for you to draw it this way, rather than to try to show the molecule all fancy in 3 dimensions, would be to form the ring either on top or on the bottom. Actually, let me try that again. Give myself enough space to draw both enantiomers here. So if the oxygen comes in on top, if the methyl and the ethyl are pointing away from me, those would still be pointing away from me. The isopropyl and the other methyl would be potentially in the plane. Or you could draw the epoxide in the plane, and then as long as you keep groups on the same side or same facing direction as they were initially, you should end up with the correct stereochemical alcohol. So those two are the same. The oxygen could have come in from the bottom. So on an exam, you could just write plus enantiomer since the two products are enantiomers. In this case, if you wanted to draw it, you could put the oxygen coming down off that where that pi bond was. The methyl and the ethyl would still have to be on the same side. And then the isopropyl and other methyl will be on the same side. Or you could put the epoxide in the plane, in which case you'd have the methyl and the ethyl again still on the same side, and the isopropyl and other methyl group also on the same side. So we were saying this last time, epoxides are really useful synthetically. Because of the ring strain, they're relatively unstable. But as we said, they're kind of in a sweet spot where they're not so unstable that it's extremely difficult to form them, or when they do form, they react right away. So they're stable enough to usually be isolated and analyzed by NMR and have a relatively decent shelf life. But because of the ring strain, they can pretty readily open up in the presence of a nucleophile. Right? Because the oxygen is electronegative. It's pulling these electrons away, creating some partial positives here. Maybe if one group's more sterically hindered than the other. If my nucleophile is strong and unstable with its negative charge, it should be able to attack right away, and when it does so, it should do so from the less sterically hindered side. And there are a variety of functional groups we've worked with last semester and this semester that we can now utilize to attack an epoxide and control the structure of the resulting molecule. Right? So that would result in a new bond between whatever the nucleophile is and this carbon here. When this bond breaks, that carbon is no longer bonded to oxygen, but still bonded to this carbon over here. And that carbon-oxygen bond is still there. So typically, after adding the nucleophile, you might add some kind of proton source, so that oxygen picks up a proton, produces an alcohol, but you end up with an OH usually on a carbon adjacent to whatever nucleophile you use to attack. So that can be used to alter the carbon skeleton, specifically if you're using a Grignard or other organometallic nucleophile. Right, so the Grignard has an organo or carbon metallic bonded to a metal. And whatever else is bonded to that carbon, it could be an R, it could be whatever, it could be a pi bond, it could be a ring. Whatever is bonded there, once it's sharing electrons with the metal like magnesium, you might see lithium, other organometallics. There's always a carbon sharing electrons with a metal, and since the carbon's way more electronegative, it will pull those electrons away and attack the Grignard, or attack the epoxide. And so what we said was, if the epoxide has a more sterically hindered side, we expect the carbon to attack the less sterically hindered side. So when it attacks, it would open up the ring, and now I make a new carbon-carbon bond. So whatever my Grignard was, it's now connected there. So the thing about that that's really nice is we can alter the carbon skeleton in a way that we so choose and make a new carbon-carbon bond between what was the Grignard and what was one of the, or was the less sterically hindered carbon of the epoxide. So as I said, there are a variety of nucleophiles that can attack epoxides, and oxygen with a negative can be a nucleophile. In this case, it's a symmetrical epoxide. It could attack either side, but maybe if this side had a methyl group or was more sterically hindered, it would definitely go to the other side most of the time, open that up. Once this electron pair shifts out to that oxygen, it becomes negative. So you'd want to have some kind of proton source around it to pick up that proton, and that makes ethylene glycol. The first step, would it be product favored or reactant favored? Well, that'd be really quite product favored, right? Because the negative on the oxygen versus the negative on the oxygen, not a big difference in stability between those two. The main aspect of this first step is opening up the ring. So there's ring strain that makes that higher in energy to begin with due to the torsional strain of the groups here eclipsing and the electron pairs of the bonds repelling. So opening up that ring, alleviating that repulsion, torsional strain and angle strain makes that first step quite product favored. And then the next step would regenerate an OH minus. So here we've got this oxygen with a negative versus this one. Those are pretty similar, so that would probably be an equilibrium where I'd have shifting back and forth. Although the equilibrium should favor the product side, since this oxygen of the OH group as a molecule is smaller, more solvent molecules with partial positives can attract there, versus here there's a little bit of sterics around that, and so that might make it harder to solvate. On the other hand, this molecule now has the ability to form an intramolecular hydrogen bond. So if this bond rotates, so these two oxygens like on the same side, or maybe gauche, one would be in the plane, the other might be out of the plane, so they're at least not eclipsing. There might be enough of an attraction there to form a pretty decent intramolecular hydrogen bond. So maybe that's more stable. So it's hard to say for sure, but these two sides are similar in stability enough where that would at least form an equilibrium. So to then shift that toward the product side, you might even add H3O plus instead of water, because that would be especially unstable and that would definitely provide the proton you need to form this product. And then instead of even forming OH minus, you'd form water as your byproduct after the H3O plus is added. So we've been harping on this idea for a while that alkoxides are not good leaving groups, right? If I had a regular ether that wasn't part of a ring, right, rather than the epoxide, I would not expect the OH minus to be able to attack that carbon and push out this oxygen. Because an oxygen with a negative and an R group, usually the sterex is going to make that relatively unstable compared to an OH that's smaller and can be effectively solvated by solvent molecules bringing in some partial positives to attract. So that wouldn't usually be a reaction you can rely on to produce much product. So the key thing here, as we've been saying about the epoxide that makes it so useful, is it's got the ring strain, which means its initial potential energy is higher and it's more reactive, right? And we can see that from the reaction coordinate diagram. The epoxide starts off higher in energy versus an ether, right? So an ether, a similar ether to that epoxide might just be dimethyl ether, right? So there's no ring. I've got two methyl groups here. There's really nothing unstable about that. It doesn't have any formal charge. All the noble gas configurations are complete. Lots of nice strong sigma bonds. So ethers are really quite stable. In order to get them to react, I need a very large amount of activation energy, so they almost never react with an OH minus. The ring of the epoxide, though, as we said, there's torsional strain. So there are groups here, just hydrogens in this case, but if there are R groups, they'd have even more torsional strain. Groups eclipsing on adjacent atoms, their clouds start to repel, and more importantly, the clouds of the bonds themselves around the oxygen and the bonds around the carbon, they're all kind of packed together tightly in that ring, and that repulsion makes it unstable as well. So since it's unstable to begin with, only a relatively small amount of activation energy is needed to reach the transition state and make the product. So this is a kinetic issue and a thermodynamic issue. Kinetically, because the activation energy is lower, and thermodynamically, because when we compare the reactants versus the products, in the case of the ether versus the products, there's a slightly lower energy for the reactants, and so the reactants are lower in free energy. So to get to the products, I need to increase the free energy, which means it's not going to be product favored if it's a positive value for delta G. Since the reactants are higher when I start with this high energy unstable epoxide, to get from there to the products, I would have a negative value for delta G. So it's product favored, and kinetically it will happen often, versus the ether that's reactant favored and kinetically quite slow. So we don't expect ethers to typically react with a negatively charged oxygen, but we do expect epoxides to react with a negatively charged oxygen through an SN2 type substitution where the nucleophile attacks the carbon, opening up the ring. And if you look at the experiments, you can see not just negatively charged oxygens of an OH or an OR, we can also get a negatively charged carbons. We can get a hydride. We can get a negatively charged sulfur. So any of these nucleophiles, which are all considered to be strong nucleophiles, because they all have a full negative charge on an atom that can very readily share a pair of electrons with a carbon, any one of those can use its lone pair to attack and open up the ring. And so now we can create structures that have a lot more variety. We can put pretty much any grouping of atoms that could potentially be a nucleophile on a carbon that's one carbon away from an OH group, because when the ring opens up and that negatively charged oxygen picks up a proton in the second step, it'll become an OH. So now we have a lot more options for syntheses, and we want to make sure we understand the regiochemical and stereochemical outcomes of these reactions. So in terms of the regiochemistry, we expect the nucleophile to attack if it's strong, and it attacks without this oxygen needing to be protonated. It should attack the less sterically hindered side. So when I have a strong nucleophile, it's sterics that mainly determines the site of attack or the region or the regiochemical outcome. So in that case, when that opens up, let's just number these carbons 1, 2, 3, 4. If the nucleophile comes in and attacks carbon 1 because it's less crowded during the transition state, there's not as much repulsion that would occur. Carbon 1 would then be bonded to the nucleophile because it's coming in and forming a sigma bond there. Carbon 1 would no longer have a bond to the oxygen, that would open, but carbon 2 would. There'd be 3 and 4. The water here would provide the proton necessary to make that an OH, and that would be the predicted product. So there's no stereochemical issues in that particular reaction because there's no chiral center produced in the product. So let's take a look at this example. Here we have a tertiary versus a secondary. So the secondary site has less sterics. We also have a specific stereochemical, a specific stereoisomer. Right? This carbon here has a specific stereochemical configuration. We could determine what it is real quick. The oxygen would be priority 1, then this carbon, so going from 1 to 2 to 3 clockwise with the fourth priority group pointing away would make that R. Here, priority 1 be the oxygen. This carbon would take priority over that one because there's more things substituted that have a higher atomic number. So it'll be priority 1, 2, 3. Going counterclockwise would make that one S. So I would definitely expect a nucleophile, since it's strong and the oxygen is neutral. The neutral oxygen does attract these electrons pretty strongly because it's more electronegative, but not so strongly to pull them away a lot to create like a lot of partial positive here. It's a significant amount of partial positive produced at both these sites, but since it's a strong nucleophile, it would be sterics that determines where it attacks mostly. Would come in there and open this up. So there's no reaction occurring here at this tertiary site. So when we draw the product at that, we don't expect there to be any change stereochemically. The methyl group should still be pointing away, and the oxygen should still be pointing out. The water would, in a second step after all that occurs, protonate that oxygen. When the nucleophile comes in here, since this oxygen is already shown with the solid wedge, it's blocking the front or the top or the area that's facing out toward you. So the nucleophile would have to come in from behind. So I would end up with the nucleophile having a dashed wedge. There was a hydrogen here, and when the nucleophile comes in, it's going to push that hydrogen forward. So you can draw it if you wanted, but you don't have to. but there's a specific both regio and stereochemical outcome here. Regiochemically, we expect any strong nucleophile to attack an epoxide from the less sterically hindered side. Stereochemically, if there is a specific spatial positioning of the oxygen of the three-membered ring, the nucleophile has to attack from the opposite side spatially and end up with the opposite type of wedge there. So this gives us two chiral centers, both of which have specific spatial arrangement of the atoms. We wouldn't write plus enantiomer here because we're not producing the enantiomer unless we started with the enantiomer of the reactant. All right, so if you're under acidic conditions, things can change a little bit. So we want to make sure when you're thinking about epoxides, the first thing you want to ask yourself is how strong is the nucleophile, and is the oxygen of the ring going to be protonated? So if there's no acid, it's not going to be protonated, and the only way it will open is if there's a strong nucleophile, right? So we don't add an acid here. As long as our nucleophile is strong, it'll just come right into the less sterically hindered side and open up the ring. If you have an acid present, like HCl, HBr, HI, and you're using an acid, and the conjugate base of the acid is going to be your nucleophile, well, you don't really have the strong nucleophile until the oxygen picks up a proton. Once the epoxide is protonated, the oxygen becomes way more electronegative. It's already the second most electronegative atom. Once it's positively charged, it attracts shared electrons way more than it normally would, creating a really large partial positive. So any nucleophile, if it's a Cl minus, Br minus, I minus, or even a water or something that's a weaker nucleophile, or an alcohol, something that's a weaker nucleophile, once this oxygen is protonated and these carbons take on such a large positive as their electrons start to get pulled away from them, any nucleophile, even a weak one, would be likely to come in there and attack. So in this particular example, there's no difference between these carbons spatially. They're perfectly equivalent, the molecule's symmetrical, so I can show the nucleophile attacking either side. Whichever side it attacks, it would open that up, and that would give me the product. So again, I can introduce a nucleophile, two carbons, with a two-carbon link to an OH group. And just to show the mechanism for that, if I had a water or an alcohol, it'd be the same thing. So let's just do the alcohol. So if I use an acid, the first thing that's going to happen is the epoxide is going to pick up a proton. Once it's protonated and positively charged, it actually starts to break the sigma bond a little bit. It's definitely not going to fully break because that would produce a primary carbocation, which would be really unstable. But it's really pulling these electrons away from both sides to create a large partial positive on both of these carbons. So then the nucleophile, even though it's weak, would be able to attack one of those two carbons. It doesn't matter which in this case because they're symmetrical. Open that up. The oxygen of the ROH is now bonded to that carbon. When this opens up, this oxygen is still bonded to the other carbon. And so we'll call this oxygen 1. This is oxygen 2, just to keep track of where the atoms are. This would be carbon 3, carbon 4. Carbon 3 was attacked. Carbon 4 is still connected to this OH. And so the ROH is what attacked, carbon 3. And so in the last step, another ROH, we have to pick off that proton to balance that charge out. So then between carbons 3 and 4, there'd be an OH on one, and an OR on the other. So in essence, I've made an ether and an alcohol on the same structure. If I used water instead, then I would just have a hydrogen here instead of the R group. And so I would make a diol. And this is the reaction we showed last semester in which you can make a 1,2 diol or 2 alcohols on adjacent carbons. That structure specifically is ethylene glycol, and this reaction is the main way that ethylene glycol is made industrially. First they make the epoxide, then they react it with H3O plus to make the diol. All right, so we want to look at the regiochemical issues here. If you're dealing with an acid, right, so this is different from if we don't protonate the epoxide. If we don't protonate it, if it doesn't have a proton and it doesn't create a positive charge, we expect a strong nucleophile to be able to attack the less sterically hindered site. Well, but what are the experimental results if we use an acid to protonate the oxygen first before the nucleophile can attack? Right, that's going to create this, and if it happens down here, similar situation. Once that's protonated, sterics is no longer the primary factor that's going to affect the outcome. Because once it's protonated, the oxygen becomes extremely unstable and it starts to pull electrons away from the carbons that it's connected to. If the carbon that the oxygen is connected to is tertiary, it will be especially good at pulling those electrons away, almost like a sigma bond resonance. Normally we only think of resonance occurring with pi bonds. There's a few examples where there's similar phenomena. It's pretty much the same as resonance, where a sigma bond isn't really a full bond, it's more of a partial bond. Because the oxygen is so unstable with that positive, it starts to pull those electrons away as a lone pair. And because this is a tertiary carbon right here, it can stabilize a carbocation pretty well. So it's not like the bond is completely intact, and it's not like the bond is completely broken. If specifically there's a tertiary site, the reality of that situation looks more like this. So we'll come back to those other sections. But basically what's happening is the bond is partially breaking, so it still has some electron density there, blocking the nucleophile from attacking that side. So stereochemically, whatever the nucleophile is, if it's a chloride or a bromide or a water or whatever, it has to come in from the back side to push that out completely. So stereochemically, I can't have the nucleophile approach and end up in the same spatial positioning of where that oxygen was because it's still somewhat blocked. But regiochemically, if that oxygen were protonated, I would expect the nucleophile to come to the less sterically hindered side. Once I protonate it, though, as we said, if one side is tertiary, that side will start to break, and a much larger partial positive will form there, and that will attract the nucleophile into that site. So the outcome we expect it to get here, and what we actually observe experimentally, is that the X, specifically the halide nucleophile, comes in on the tertiary carbon. I can imagine it coming in there or there. Either way, this is the carbon that X ends up bonded to, not the other carbon. If the carbon is secondary, then the degree to which that happens is pretty minimal, because the secondary carbocation is not really that stable. So this oxygen, once it's protonated and forms positive charge, it doesn't really do much of a shift of the electrons out. It doesn't really create that much more partial positive here versus over here. So in that case, it's still sterics that determines the outcome. And it'd be difficult to predict this, right? If we're just guessing what would happen, I wouldn't expect you to know. So the results here are from experimentation. So what you see experimentally is the nucleophile attacking the side that's less sterically hindered. That's usually where it ends up. So if we're trying to predict the outcome here, the question is, or really what it comes down to is, sterics is the main factor. That's always going to be the major factor when you have a strong nucleophile and you do not have a protonated the epoxide. The electronic effects, and by that we're referring to this effect where the carbon-oxygen bond of the ring already starts to break and draws in the nucleophile to that more sterically hindered carbon because of the electronics or charge involved. That really only is a factor when two things have occurred. You've protonated the epoxide first, and it's a tertiary site. So you definitely want to try to remember those two conditions have to be met to entice the nucleophile into the more sterically hindered side. Otherwise, it will go to the less sterically hindered side. So is the mechanism SN1 or SN2? Well, specifically, when you're using an acid to protonate the oxygen, whatever that structure exactly looks like, once the oxygen is protonated, it will start to attract these electrons. But as we said over here, it's not fully breaking and creating an actual carbocation. If this were occurring, it would be more of an SN1. If the nucleophile were attacking on a full-on carbocation that's flat and open, it could attack equally as often from the front or from the bottom. If that's what we saw, and spatially, stereochemically, half the X's came in from the top connecting with the solid wedge, and the other half from the bottom connecting with the dash wedge. If that's what we were seeing, we could conclude it was an SN1. But that's not what we're seeing experimentally. Right? So whatever the nucleophile is, it cannot come in from the top. We're not forming a carbocation. All of the product that you observe involves a nucleophile spatially positioned opposite of where the leaving group was connected. Right? So if the oxygen that's going to be breaking here as the nucleophile attacks, that bond's breaking, that bond has a solid wedge. It's occupying the side of the molecule facing out at you. That means the oxygen has to come from behind, and that's where it ends up. So in that regard, it's like an SN2. It's like an SN2 because we always see a backside attack. We don't form a carbocation. We don't see the nucleophile coming in from the same side where the leaving group left. But it's also not like an SN2 because in an SN2, what we normally see is the nucleophile can't attack a tertiary carbon because it's too crowded. Right? This is a tertiary carbon. Normally it's too crowded for any nucleophile to get in there. So what allows this nucleophile to attack is really that we have something here that is kind of like an SN1, but also kind of like an SN2. It's kind of in between both of those mechanisms that we saw. Right? So it has the characteristic of an SN2 in that the nucleophile has to come in from the backside from where the leaving group's leaving. But it doesn't match with this other characteristic of an SN2 because normally if it were SN2, there'd be too crowded for the nucleophile to come into the tertiary site, but we do see it coming into the tertiary site. And that's more reminiscent of an SN1. Right? So what is similar in in this mechanism to an SN1 is that we see the nucleophile actually attacking a tertiary site. So it's kind of like an SN1, kind of like an SN2, and that's what leads us to this picture here. Again, because the oxygen is partially breaking this bond, it allows these two methyl groups to kind of swing up out of the way a little bit, spatially. So even though it's tertiary, because the oxygen is kind of pulling some of the electron density away here, that electron density doesn't repel these methyl groups as much, they kind of swing up out of the way, and that's what allows space for the nucleophile to come into a tertiary site, which normally wouldn't be possible until a carbocation forms there. But we're not forming a carbocation because the oxygen isn't fully pulling away. And since it's not fully pulling away its density, its electron density, there's no way for the X group to come in from the top because that electron density is already there. It has to come in from the backside. So we have the backside attack feature, which is reminiscent of an SN2, but we also have it attacking a tertiary carbon, which is reminiscent of an SN1. Any questions about any of that so far? All right, so what we want to do is to pay close attention to stereochemical outcome. Last semester we learned how if you have an epoxide and you want to open up and create a diol, you can use water and H3O+. This semester we've learned you can also use water and OH-. Which set of conditions do I want to use? Well, the answer depends on the stereochemical outcome, right? So when one side is tertiary, I can get a nucleophile to come into that side and push out the leaving group, but only if I protonate it first, which means I would need acidic conditions. So what I have to look carefully here is one of these two carbons is going to remain connected to this oxygen with a solid wedge. Because whichever nucleophile attacks, it's going to have to come in from the backside to one of these two sites. And whichever site it comes into, it's going to be connected with a dash wedge. But the oxygen is going to still remain connected with the solid wedge to whichever carbon isn't attacked. And so when I look at the product, you see, okay, there's the oxygen with the solid wedge. That must have been this oxygen, which means I'm not having the attack occur here. If I used a strong nucleophile and don't use an acid to protonate this first, I would definitely expect that to come in from the less sterically hindered side. And if that occurred, that OH would end up connecting there, and it would have to come in with a dash wedge and to push that oxygen out. It would end up with a dashed wedge there. And then if that happened, there wouldn't be any change there in that oxygen or in the methyl group. Obviously, the oxygen would be negative. It would pick up a proton from the water to make an OH. So I would get a different stereochemical outcome than the one I'm trying to make. So that tells me these are not the conditions I want. If I want the nucleophile to attack the more sterically hindered side, the tertiary side, the only way I can get it to do that is if I use an acid to protonate that first, in which case it will start to leave, open things up a little bit, and allow the water to attack that side. When this oxygen breaks away here, it will remain connected here, so I'll still have the solid wedge there, like I want, if that's the product I'm trying to make. And when this water comes in, it will have to come in from the backside, so once it's deprotonated, it will produce an OH there with a dashed wedge. And that will force this methyl group forward. So you really got to pay close attention to the stereochemical outcome. That will determine which set of reagents to use, whether you're depending on the spatial position of the groups that you want to make in the product, right? So if you want the attack to occur at the less sterically hindered site, use a strong nucleophile and don't protonate the oxygen. If you want the attack to occur at a tertiary site, use an acid to protonate the oxygen and then whatever nucleophile that you need to attack. All right, so that finishes up the section on epoxides. Please let me know if you have any questions about that. So now we're going to talk about sulfur a little bit. Sulfur is not the most common element in organic compounds, but it's definitely is critical to life. It's found in certain proteins, and it's definitely critical to some molecules, pharmaceuticals, and other types of structures that organic chemists might want to create or synthesize. The main issue with sulfur is that it stinks. Literally, it smells really bad in most organic compounds. So if you make an organic compound that has a sulfur in it, chances are, if it's volatile and it has the ability to evaporate, it's going to smell pretty bad. So we try to generally avoid that unless we really have no other option. But in terms of looking at sulfur versus oxygen, and when you look on the periodic table, they're in the same column. They have the same number of valence electrons, so when they bond in there, they're basically going to be interchangeable. If I replace an oxygen with a sulfur, I don't have to do anything else to the structure to make the noble gas configurations complete and avoid formal charge. There will occur a change in the name. So when you're naming sulfur-containing compounds, if your compound has an SH instead of an OH, then you just change the suffix from all, as in butanol, indicating there's an OH on carbon 1, to thiol. And just because I think they think it sounded better phonetically, they put the E back in. So that's confusing. But I guess they didn't like the way butanethiol sounded. They wanted to be butane thiol. I don't know. There's maybe some kind of argument they may have had about that when they were coming up with the name system. I don't know. But that's the system we have. So try to remember that. It's probably not something I would take off for in a naming question, as long as you got the suffix right and the rest of the name correct. Sometimes you might have to name it as a substituent instead of part of the parent chain. So if I'm numbering this one, 1, 2, 3, 4, the OH takes a priority over the SH. So that would be 4 carbons, gives me but, and I've got an OH on carbon 1, so it's 1-butanol. Obviously I have a methyl on 3, and then I have this SH on 3. And so to name an SH group as a substituent, it's not a thiol, it's a mercapto group. And that's similar to when you have a chlorine or a bromine. If it's a substituent, the O is there to indicate it's a substituent. If it's a carbon substituent, we put a YL suffix. If it's an oxygen, if it's a sulfur or a halogen substituent, we put an O there. So mercaptans is exactly the same as saying thiols. These molecules that have an SH somewhere connected to a carbon. The sulfur's lone pair is especially good at forming ion dipole type attractions or London force type attractions to mercury atoms. And so they're called mercaptans. This compound here especially is used to treat mercury poisoning. So let's see if we can draw that and explain that phenomena. So I would start with the parent name, 1-propanol. So this would be carbon 1, 2, 3. 1-propanol, there's an OH on carbon 1. And on 2 and 3, there's a di-mercapto. So I've got a mercapto on 2 and a mercapto on 3. That means I've got an SH here and an SH here. And what that does for mercury poisoning is it spatially positions these lone pairs at just the right distance to bond to a mercury. Usually if you have mercury poisoning, usually it's because of mercury ions, and those can find specific sites in your proteins to bind and cause the proteins to fold improperly or block out their active sites so they're not able to catalyze reactions in the body the way they should, and that can cause a lot of health problems. So if you take this compound, which probably stinks really bad, and use that as a medicine, obviously you would do that as directed by a doctor, the attraction there can kind of sequester the mercury, and it attracts so well to this molecule that can be excreted rather than the mercury staying and potentially accumulating in your body. Skunks produce a thiol. That's this. If you smell a skunk, it's because they produce a compound that contains a carbon bonded to a sulfur bonded to a hydrogen. And the one that they produce, I don't know the exact structure of it, but it's definitely volatile, right? It has to be able to evaporate if you're going to be able to smell it. So there's also a small amount of methane thiol that's added to natural gas. So if you ever smell a gas leak, or if you smell the gas in the lab as it comes out, it's not because methane actually has a smell. Methane is odorless. So if you had a gas leak and methane was leaking and it's explosive and it's filling up your house, creating explosion risk or even potentially suffocating you, because if it fills up so much, you're not getting enough oxygen. It could potentially cause asphyxiation that way, but you wouldn't know because you can't smell it. So a tiny amount of methane thiol is added to methane, and that only takes a very, 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 very small amount for you to detect it if it's present. So you can lay your paranoia to rest, Cindy. There shouldn't be any situation where you have a gas leak that you couldn't smell, because this is, for some reason, humans have evolved to smell these types of compounds even in very, very tiny amounts. And if it's there, if you have a methane leak, you should probably detect it unless you personally have an extremely dull sense of smell. So one issue related to these types of thiols is if you want to make them, you can get this hydrogen sulfide ion, and it's a great nucleophile, right? We already know that sulfur, being a relatively large atom, is really good at sharing electrons with carbon. It is a base, but it's not a very strong base, so it's a much better nucleophile than it is a base. And that's what we're going to see as we go through here, and we're going to see how you can use that to do some synthesis if you need to make a thiol or a compound that contains sulfur. As a small, relatively strong nucleophile, we definitely expect it to do substitution rather than elimination. It's not a great base. It is a base, but it's not a very strong base, so we don't expect it to be picking up protons. We expect it to be attacking carbons. So if I have a primary carbon, I expect the negatively charged sulfur to attack very readily and produce a thiol. There's no change in the carbon skeleton when a thiol attacks or a hydrogen sulfide attacks. If I have a secondary carbon, I still expect the same. So if I had a negatively charged oxygen here, then I have a problem, because this is a good nucleophile. It could come in and attack, but it's also a good base. It might pull off a beta hydrogen and do elimination. So what's nice about the sulfur is the elimination is very minimal. You can basically ignore the elimination that might occur and just expect the thiol to come in, or the sulfide to come in and push out the leaving group. And since this occurs by NSN2, if the leaving group is positioned in one direction spatially, the SH minus would have to come in the opposite direction from that, ending up with the opposite spatial positioning. So we're talking about how SH minus is not a very strong base, and we can quantify that by looking at the pKa values of its conjugate acid. So if I put this thiolate ion in water, there's a possibility it could pick up a proton from water. If it picks up a proton, it will now have that proton connected, and the water will have lost a proton, so the water will become OH minus. That could also obviously go back and transfer the proton back to the other side. So if we're looking at an equilibrium and we want to predict, especially if it's an acid-base equilibrium, which side the equilibrium is favored, we would look at the pKa of the acids on both sides. So most thiols have a pKa of about 10 to 11, and water's pKa is 15 or 16. So you got about 5 to 6 pKa unit difference. So if I subtract the pKa's of the two acids on both sides of the equilibrium, the result I get quantifies the difference in how much one side of the equilibrium is favored over the other. So does that mean that one side has 5 times more than the other? No. Right, the pKa scale is a log-based scale. So really it means there's 10 to the 5th or 100,000 times more of the substances on the side with a higher pKa versus the substances on the side with a lower pKa. So the thiol, once it's deprotonated and creates a negative charge, is not very good at picking up a proton, because when it does, it produces an acid that's got a relatively low pKa, especially compared to water, and so it'll just shift back. Now, if I have a sulfide and I add H3O plus, that will protonate it. Because if the sulfur picks up that proton and the H3O plus loses a proton and become water, now we're comparing the pKa of H3O plus, which is close to 0, versus the pKa of this, which is around 10. So now we have a situation where that's pretty much 100% shifted toward the product side versus the reactants. So if you want a naked sulfide with a negative charge that can attack a carbon as a nucleophile, water is okay. Water won't effectively protonate it, because then the OH minus would just pick that proton back up and you'd regenerate that great nucleophile. If you want to protonate it though, all you need is a significantly stronger acid, something with a lower pKa, much lower pKa than 10, and that is obviously H3O plus will be fitting the bill there. So picking up that proton could definitely protonate that if you want it to be protonated. So there's also something called a disulfide. I'm not going to spend a lot of time on this. I probably won't ask you about this mechanism, and I don't think I even included this set of reagents on the list of reagents that I recently added to your formula sheet. And by the way, I made some changes to the formula sheet. I added a bunch of reagents, a list of reagents at the end. So you want to print that out and have that with you on the exams if you want to take advantage of that. But basically what happens here is if I start with a sulfide, add Br2, it'll act as a nucleophile, pick off a Br, but then that's a good leaving group. So another molecule of the original sulfide, there'd be multiple of those around, it would attack the sulfur and push out the Br leaving group. And so then I have this sulfur-sulfur bond. It's not the most stable bond. It's got a relatively low bond dissociation energy. So this can break open and form free radicals. But it's at room temperature, relatively stable. You need a little energy to break that up for the most part. So there aren't a lot of disulfides in organic chemistry. They're mainly because they're not that stable, and also, as far as I'm aware, there's not a lot of uses for them either. However, this is the type of bond that is used to vulcanize rubber, I believe. These disulfide linkages. So, if you have these long polymer chains and they're all tangled up, their London forces are holding them together. It's hard for them to slide past one another. But if you want to make the material harder and more rigid and more resistant to falling apart, if you design the polymer to have some sulfur atoms along its chains, then you can set up a reaction like this by deprotonating them and using Br2 to pull off the protons and then connect the sulfurs together through this sulfur-sulfur linkage. And then by connecting all the chains up through these covalent linkages, it rigidifies the polymer structure, makes it harder, makes it more resistant to damage, which is obviously what you want, especially in Ohio with all the potholes we have. Yeah, I'm not going to go into too much more detail there on disulfides. Probably won't even ask you about them. So the other type of functional group involving a sulfur are the sulfides or thioethers. Right? So we saw thiols. That's where I have one R group connected to the sulfur. That's analogous to an alcohol, just replacing the oxygen with sulfur. The sulfides are analogous to ethers. All right, we talked about ethers at the beginning of chapter 14. We have two R groups on either side of an oxygen. If we replace that oxygen with a sulfur, now we're talking about a group of compounds, functional group called sulfides or thioethers. So that's the thing about sulfur. There's usually more than one name for things. So when we talked about naming ethers, we said there's two ways to name them. We can name ether as our parent name and then name both substituents. If they're both ethyl groups, it'd be diethyl ether. And so since replacing the oxygen with the sulfur makes an analogous compound that's called a sulfide, we would just call that diethyl sulfide instead of diethyl ether. A lot of times, though, trying to name both substituents on either side of the oxygen creates a challenge. So rather than just taking the oxygen as the parent name and naming both R groups as substituents, what you'll often see instead, as we talked about earlier, was naming one of the substituents on the oxygen as a parent. So that's cyclohexane parent. On that parent, on carbon 1, you've got this methoxy, right? It's a methyl group, but the extra oxygen makes it a methoxy. And then on carbon 4, you've got 2 chlorose. So if we do the same structure but replace the oxygen with the sulfur, we would name it the same way. We would have the same parent chain, the cyclohexane. We would number it the same way. We'd still get the sulfur priority over chlorine. So we have 2 chlorines on carbon 4. And the group now here, it's not a methoxy because we have oxygen. It's a methyl thio. So it's a methyl group, but that extra oxygen or extra sulfur there is why we have a thio. It's kind of like a thiol, but it's just a thio. So that's the slight modification you'd make there to the naming of sulfides. So how do you make a sulfide? Well, it's actually pretty straightforward, right? We already know that sulfur that's negatively charged makes a really nice nucleophile. So how do we make that? Well, we just showed if you have a thiol, NaOH should be strong enough by about 5 powers to 10 to pick off that proton, leaving the electrons behind on the sulfur, making it negatively charged. So I can make a sulfide from a thiol using OH minus. Then that sulfide becomes a great nucleophile. So in our group that has a leaving group, that could potentially attack, push out that leaving group. And the nice thing about this is this molecule is not very basic. So it's quite weakly basic, which means I don't have to worry about it picking off a beta hydrogen and doing elimination. It's pretty much exclusively going to do the substitution I need, pushing out the leaving group to make the sulfide or sulfur analog of an ether. So that brings us to our first quiz question. Now that we have the background necessary to solve this, combining what we talked about today, and prior to that, we can fill in these boxes. So the first one here, pretty straightforward. There's really only one way to make an epoxide that we talked about, and that is to start with an alkene and use MCPBA. Or if we didn't have this here, we could have used the Br2 in the dark with H2O followed by NaOH. We talked about that as an alternative to MCPBA. Okay, so once we have the epoxide, now that we know what to do with that, if we want to open up the epoxide by having some nucleophile attack the less sterically hindered side so that the oxygen remains connected to this carbon, which is what we want in both of these reactions, starting from the epoxide. We want to retain that bond there. We don't want to add an acid and protonate it. If we add an acid to protonate it, that bond will start to break, and that will attract the nucleophile into the large partial positive that would form there. So we just need a strong nucleophile to come in here. So what nucleophile do we need? Like if I can't tell what it is, I want to start drawing in the hydrogens in the area where the reaction's occurring. And I want to number the carbons. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So in this reaction, the carbon number isn't changing. But on carbon 2, there was only one hydrogen to start with, and now there are 2. So I need to install hydrogen, and it needs to be a nucleophile. It needs to be able to bring in electrons. And so that would be LAH. And then I would need some H3O plus potentially to add that proton. Right, so what's going to happen here is the LAH is going to deliver a hydride into that less sterically hindered side, opening that up. That's going to bring the new hydrogen in there. When that opens up, this oxygen's still connected here, but it becomes negative. So if I wanted OH, that's why I add the H3O plus in the second step. I can't add this all together, obviously, because then the hydride would just pick up an H from the H3O plus to make H2 gas. So the H3O plus has to be added in a second step so that oxygen can deprotonate it and become the alcohol. So what's happening over here? Well, clearly here I need to bring a sulfur in, and I need to attack this carbon, which is this one, right? So if I number these carbons, I'll number the sulfur 2, 6, 7. So I need to add 2 more atoms, and I need the sulfur to attack carbon 2, which is great because carbon 2 is the side I would normally expect a strong nucleophile to attack as long as this oxygen isn't protonated first. So 1, I add the sulfur. There's no reason why I couldn't start with that sulfur connected to the carbon. So I saw some people using an SH minus and just bringing the sulfur in with the hydrogen and then later deprotonating that and having it attack a methyl group. That's fine. But in fewer steps, assuming this is available, if I start with the methyl group connected to the sulfur and I make that negative, it would involve a sodium spectator ion, the sulfur would attack carbon 2 and open that up and it would be connected there. That oxygen would still be negative though. So in a second step I might use some H3O plus to protonate that oxygen. And then the last box here, what's going to happen if I treat this with HCl? Well, pretty straightforward. That oxygen is going to pick up a proton from the HCl, making it a good leaving group. And since it's on a tertiary carbon, nothing can really attack yet. It has to leave first. And when it does, it'll create the most stable carbocation that can be made, so there won't be any rearrangements. But then the Cl minus, which is a pretty good nucleophile, would come in there and attack it. So I would expect to have a Cl there. And since I don't have any chiral centers here, I don't have to worry about using dashes and solid wedges to indicate spatial arrangement. Any questions about that one? All right. So once you have a sulfide, it can be oxidized. And I'm not going to spend a lot of time on these. The mechanisms for these are not anything the book really even goes into, so obviously I wouldn't expect you to know them. And this is probably where a little bit of memorization might come in, but I did put this reagent on the formula sheet as well as this one here. So you just have to remember which of those two sets of reagents does what reaction. And if you oxidize one level of oxidation, you get a sulfoxide, and the reagent to make a sulfoxide is the NaIO4. Should still be a lone pair there. If you want to oxidize it all the way up to the sulfone, which I think is a cool sounding name, you'd use hydrogen peroxide. That's a pretty reliable way to put 2 oxygens on that sulfur and convert it into a sulfone. So depending on the structure of the molecule you're trying to make, you might want to make a sulfoxide or a sulfone functional group. Just to point out, there is resonance in these. So anytime 2 atoms have a pi bond, where one atom's more electronegative than the other, we could imagine the pi bond shifting to create an alternative resonance contributor. And when we were talking about carbonyls, we said shifting these electrons out here to create an alternative resonance contributor created a situation where one resonance contributor was much more stable than the other. Right? This is way more stable. So when we draw a carbonyl, we never draw it like this, because this is a very minor resonance contributor. It's significant because it helps us understand why the carbon and oxygen carry so much positive and negative charge, respectively, in addition to the induction that shifts electrons away. But it's not a very major contributor, so we pretty much always draw a structure like this. When we substitute the carbon for a sulfur, we actually see the opposite. So looking at these two structures, comparing them to these two structures, as we said down here, there's a massive advantage. The carbon here has a noble gas configuration, which it doesn't have over here. Here, there's no formal charge, and that's not the case over here. So there's 2 major reasons why this is much more stable than the minor contributor. With the sulfoxide and also with the sulfone, there's a couple other issues that are relevant. And one is the noble gas configuration of the sulfur is really only complete over here. So despite the formal charges, having the sulfur with a complete noble gas configuration is a little bit more stable than having it have more than 8 valence electrons. Carbon can never have more than 8. It'd be way too unstable to even consider that. But sulfur, having an extra energy level, can hold more than 8 valence electrons in the third energy level, versus obviously carbon can't have more than 8 in the second energy level because there's only space for 8 in the second energy level. So both of these are pretty reasonable from that perspective, right? This one has the advantage of not having any formal charge, and it's okay to give the sulfur more than 8 valence electrons. This one has the advantage of having complete noble gas configurations for both atoms, even though it has the disadvantage of having these unstable formal charges. So really the other factor has to do with orbital overlap. When we think about the carbon-oxygen, right, there's a sigma bond, oxygen. There's a sigma bond holding the electrons between the nuclei. That's relatively stable, and that's true in either resonance contributor, right? There's a sigma bond here that's not breaking, so that's not really relevant. What's important is the p orbital overlap. When carbon and oxygen make a pi bond, the p orbital on the carbon and oxygen are both in the second energy level. And so they line up pretty well and overlap pretty effectively. But when I replace that with sulfur, because sulfur's valence electrons are in the third energy level, it has a bigger, more elongated p orbital, and its third energy level sigma bond is also bigger and more elongated. So the oxygen, which can form a nice sigma bond here, but the oxygen's p orbital is not big. So it can't really get close enough to effectively overlap with the sulfur. So when I have two elements that are in the same energy level, their p orbitals overlapping side by side works out pretty nicely. But when they're in different energy levels, the mismatch of the sizes of the p orbitals and the distance between them because of the extra large orbital shapes for the third energy level versus the second means that there's not a good orbital overlap here. So the pi bond is just way less stable than a typical CO double bond. Pi bond, the SO pi bond is not nearly as stable. So actually, in this case, this is the major contributor and this is the minor. And what that means is these sulfoxides and sulfones are a lot more polar because the major contributor actually has formal charges. The resonance hybrid is going to look more like the major contributor, and they're going to be even larger quantities of partial charge on both the oxygen and the sulfur in each of these structures for that reason. So you might ask you a question about that. These, especially, if I put a couple methyl groups on that sulfur, this structure is one we talked about last semester. It's DMSO. DMSO is a great polar aprotic solvent. It's a great solvent for SN2 reactions. It's very polar. There's very large quantities of partial charge there that really help to interact with charges that might form during transition states and stabilize them. So DMSO is a great solvent. The problem with DMSO as a solvent, though, is that because there's so much charge and it's so polar, it has a very high boiling point. It's not very volatile at all. So it's very difficult to then remove that solvent through evaporation at the end. It's the biggest drawback of it. If you recall, when we talked about ozonolysis reactions, we said we're going to use O3 in one step, and then a second step, DMS. And we really kind of glossed over that, didn't focus on it much. But the DMS stands for dimethyl sulfide. And the reason that's added and important in the ozonolysis reaction is the sulfur of that sulfide ends up picking up an oxygen and becoming a sulfoxide. And that step is what then actually cleaves the two carbons finally away from one another, creating the CO double bonds that we normally think of resulting from an ozonolysis reaction. So that was a bit of a throwback. All right, so let's look at a quick synthesis here. Let's say we want to make the sulfoxide. If we want to make the sulfoxide, we would probably assume that that's going to be formed from a sulfide. So how do I make a sulfide into a sulfoxide? The NaIO4. If I used the hydrogen peroxide, I would make that all the way into a sulfone with 2 oxygens instead of 1. So this reaction better form this, or we have issues. So let's just check it out. So what would happen here first is the OH minus would pick off this proton, leaving electrons on that sulfur. So that would make that sulfur a very nice nucleophile. It's already even pretty decently nucleophilic even when neutral. So once it's negative, it's really a very nice nucleophile. Even though this carbon is secondary and it's pretty sterically hindered, I should still be able to get this to get it, come in there and push out the bromine. So if the bromine was positioned facing out toward me with the solid wedge, the sulfide would have to come in from behind with it, and that's why it ends up with the dashed wedge. Just to quickly look at the formal charge on this sulfur. Sulfur is in column 6A on the periodic table, so it needs 6 valence electrons to balance out its formal charge. How many are actually assigned to it? Well, it's got 2 all to itself in this lone pair, 1, 2. And it's got 2, 4, 6 that it's sharing, so half of that, 6 minus 6, and, oops, sorry, 6 minus 5 gives me a plus 1. 3 plus 2 is 5, gives me a plus 1 for its formal charge. All right, so usually at the end of each chapter from here on out, we're going to talk about synthesis, and a lot of the chapters coming up also talk about spectroscopy, so we're going to definitely be working more with NMR, especially as we talk about reactions these functional groups undergo. So you'll definitely want to maybe brush up on NMR a little bit in the next few weeks. But in terms of syntheses, I know students often struggle with, how do I convert this molecule into this other molecule? And what we've been saying is we want to focus first on the carbon skeleton, right? So you might want to number the carbons. If you can find similarities in the structures where something is not changing, you want to number those. Okay, now I see here, there's an extra carbon here. So I need to install a carbon-carbon bond here. I need to connect something to carbon 2. And I see obviously there's an OH here. I need to connect that to carbon 1. Carbon 2 initially has a hydrogen, so again, drawing in the hydrogens on the atoms where there are reactions occurring, always a great idea. So I can see I don't have to add in an additional hydrogen. The one that's there initially is still there. I just need to add this here. So how do I get 2 functional groups on adjacent atoms? Well, we just talked today about a way to do that. So if I can make my molecule into an epoxide, the oxygen is already built in. So I just have to figure out what nucleophile I need to attack that and open that up. So a nucleophile will be connected to one carbon and the oxygen will be connected to the other carbon, which is what I'm trying to do here. So the first thing I would want to do here is to use the MCPBA to convert that into an epoxide. Oops, silly. I'm drawing over here. So the methyl group would still be here, and then I have the epoxide forming. So then to open that up, I would use this as a nucleophile, CN. CN It's like this, and there's a negative formal charge on the carbon. So this is a cyanide ion, sodium cyanide. Obviously, cyanide is poisonous. But as long as it doesn't evaporate, and as long as I don't drink this solution or get it on my hands and then forget to wash my hands, it's not really dangerous to work with. So the cyanide would come in. And since I've got one site that's a little less sterically hindered than the other, I can be pretty sure it would come into that side and open that up. And that would install the new carbon-carbon bond. When the oxygen opens up, it would be a negatively charged oxygen on carbon 1. So I still need to provide this proton. So in the third step, I would add some H3O plus. I wouldn't add this two together. I don't want to protonate the oxygen first. If the oxygen of that epoxide were first protonated by adding H3O plus, then it would start to draw electrons away from the tertiary site, because the tertiary site can so effectively stabilize the partial positive. That would attract the Cn minus into that site. I would get the Cn minus on carbon 1 instead of carbon 2. I would get the wrong regiochemical outcome. And so when you're dealing with epoxides, you really got to think about that. Do you want the nucleophile to attack the less sterically hindered side or the tertiary side? If you want it to attack the less hindered side, don't use an acid. Just use a strong nucleophile. It should make its way in there due to there being less sterics. If you wanted it to attack the more sterically hindered side, then you'd need to protonate the oxygen. That would be an issue with cyanide, because if the cyanide ion, which is fully charged and forms strong ion dipole interactions with solvents, so it doesn't evaporate, you don't have to worry about its poisonous characteristics unless you were to drink it. If that picks up a proton and becomes HCN, now it's neutral, that's a gas. And that can poison you from the air, so you definitely want to avoid hydrogen cyanide formation. So either way, we definitely want to avoid the acid being around when the cyanide is around. So there's some more paranoia for Cindy to worry about. All right, a couple other issues, synthetic issues. When you're dealing with a Grignard, there are really three reactions. There are really three reactions that you want to focus on for the most part that the Grignard is going to do. So one of these involves a Grignard attacking an epoxide. So if I have an alkyl halide, I can always make that into a Grignard by adding magnesium. That reverses the polarity of this bond, making the carbon go from a partial positive to a large partial negative. So it's nucleophilic, it's not stable, it'll use those electrons to attack. And so in the next step, if I add an epoxide, the attack will occur on whatever carbon is less sterically hindered. If they're the same, it doesn't matter which. It would attack there and form a new bond to one carbon, and the oxygen would still remain connected to the other carbon. So if you're looking to make a new carbon-carbon bond, one carbon away from an oxygen, Grignard hitting an epoxide is a really good way to go. And you can think about that from two perspectives. If I give you an alkyl halide, you can make that into the Grignard and then later add an epoxide. If I give you an epoxide, then you just need to think about what Grignard do you need to come up with so that Grignard can attack the epoxide and give you that specific product. Right? So part of the skill here involves looking at the product, recognizing that you need to add a group that's one carbon away from an oxygen, and then thinking back at what is the reactant that's given. Are you starting with an epoxide? Are you starting with an alkyl halide? Well, either way, you should be able to set the reagents up to make that type of product. Don't forget, you can also add a Grignard to a carbonyl. And that produces a slightly different pattern in the product. So this is where the pattern recognition is so important, right? So what do you want to look out for here? There's really a couple things. So as we said, if you want to make a new carbon-carbon bond and create a two-carbon chain between the new group and an oxygen, the epoxide route we just talked about on the last slide is a great route. So that's when you know you want your Grignard to attack an epoxide. Alternatively, if you make a Grignard from an alkyl halide using magnesium, and the Grignard creates a real large partial negative there, if you want the R group to come in and connect to the same carbon the oxygen is on, instead of an extra carbon away, that's where you use the carbonyl. So really noticing the number of carbons between the new R group and the OH is really what you want to focus on practicing. If it's 2, you want it to attack epoxide. If it's the same carbon, then you want it to attack a carbonyl, because the Grignard will come right into that carbon and push these electrons up. So the oxygen's still connected there with the sigma bond, and the R group comes in and makes a new connection, and they end up connected to the same carbon atom. So let's take a look at this one. What do I see here? I want to number these first. Clearly there is a change in the carbon skeleton, and I want to analyze that change so I get things exact here. So I've got 6 carbons initially. I need to add 1, 2, 3, 4, 5 new carbons. And what I'm noticing is this R group, which is here, is connected to carbon 7, which is 1 away from a carbon the oxygen is on. Right? So if this R group ended up connected to the same carbon that the oxygen was on, then I would want this R group to attack a CO double bond to make that direct connection. But that's not what I have here. I have the OH 1 additional carbon away. So that's the sign that we just talked about, tells you you need to use an epoxide. So the first thing I'm going to do is convert this into a Grignard. That's going to make the alkyl halide an alkyl magnesium halide, which makes this carbon nucleophilic because the magnesium wants to get rid of the electrons to make its noble gas configuration. You can also draw that like this if you want, to show how nucleophilic it is. Technically, it is sharing to some extent, so it's not technically correct to show it as a lone pair, but that's fine if you want to do that, especially for synthesis. And then I need to add these other carbons. So the next thing I'm going to add would be that carbon arrangement. 7, 8, 9, 10, and 11. And I'm going to set up between 7 and 8 an epoxide. I need carbon 1 to connect to carbon 7. Which is exactly what's going to happen here, because carbon 1 is nucleophilic and carbon 7 is the least sterically hindered side on this epoxide. Boop. Open that up. And when that opens, the oxygen here is going to be negative, so in the third step I would add some H3O plus to pronate that oxygen. All right, so what about this one that we had as our quiz question for the second quiz question for today? What am I going to do here? Well, first thing I'm going to do probably is to analyze the carbon skeleton. And I see this isopropyl group up here. It's right here as well. So I'm going to number these carbons the same way because I at least thinking that these 4 carbons are the same carbons and that what needs to be added are these other 4 carbons. So I can number this maybe 5, 6, 7, 8. So what I need to make here is a new carbon-carbon bond similar to the last problem. Just redo that real quick. So I need to make a new carbon-carbon bond between carbon 1 and carbon 7. So that means I'm going to have to make either 7 a Grignard and have it attack 1, or probably make 1 a Grignard and have it attack 7. And there are different ways to do that depending on the route you might choose. So, man, I don't necessarily know which way to go. And when I have an OH, there's so many things I can do with that. It's hard to know how to work forward. I can predict at least what the last step is going to be, because there's only one way we know of to make epoxides, and that would be to add MCPBA or Br2 in the dark followed by NaOH to convert an alkene into an epoxide. So working backwards, the very last step of the mechanism would have had an alkene between carbon 7 and 8. So that at least gets me a little closer to the reactant. I can start to think about how to make this work out. So, there's a couple different options I have here. I can think about trying to make this into a Grignard, where carbon 1 would then attack carbon 7. So that's something to consider. Or I could make carbon 1 the electrophilic site and have carbon 7 attack carbon 1. Right, so there are 2 different options there. Let's take a look at both. So just randomly, let's say we want to disconnect here retrosynthetically, and let's say we want to make carbon 7 the Grignard. I want to have it attack carbon 1. If I want carbon 7 to attack carbon 1, I need carbon 1 to be electrophilic. There's 2 ways I can do that. One is if I use PCC and dichloromethane, I can convert this OH into a CO double bond, right? That's the oxidizing reagent we talked about recently. That will make that carbon electrophilic. And then if I want carbon 7 to attack it, I could get this 5, 6, 7, 8. Oops. I'll do it this way. Let's make this 5, 6, 7, and 8. I want an alkene between 7 and 8. I'll just put that in there. And I want 7 to be a Grignard. So I'll just put that in there and just say, hopefully I can buy this Grignard. If that existed, then this carbon 7 would be nucleophilic because it would be pulling the electrons away from the magnesium. It could use those electrons to attack here, push these electrons up, and that would give me something that looks like this. Actually, let me draw that differently. I'm trying to make it look like the product. So if that comes in here and pushes these electrons up, those electrons would then exist on that oxygen. And carbon 7 would then be connected there. There'd be a pi bond there. So that's almost what I was trying to make. The problem is there's an extra oxygen on there. So I'd have to figure out a way to get rid of that oxygen and replace it with a hydrogen. That's not necessarily easy to do. We haven't really talked about any reactions to make that work. So this particular pathway, I might be able to make it work, but I probably need a lot of steps maybe to get from here to here so that I can then MCPBA that and make the epoxide in the last step. So maybe that's not the best route. So sometimes there's a lot of trial and error involved. So let's consider another option. So instead of making this a carbonyl for the Grignard to attack, what if I just put a Br there? How can I get that OH converted into a Br? Because if I had a Br there, then I could use the same Grignard. Really, it doesn't have to be a Br, it could be any leaving group. It's on a primary carbon, it's not too sterically hindered. So I would expect the Grignard to probably be able to attack it and push that out. And that would make the new bond between 7 and 1, and would only leave behind a couple hydrogens here on 1. So that would actually go right to the penultimate molecule, which would then be need to be treated with MCPBA to make the epoxide. So that looks actually pretty good. But how do I get the OH converted to a Br? Right, there's a couple different options for that. One would be to use PBr3, or I could use HBr, or I don't have to make it into a Br. I could use tosyl chloride with pyridine and make it into a tosylate leaving group. And then the Grignard could just attack that and push that leaving group out, and it would still give me the same substance. So there's a lot of options for converting an OH into a good leaving group. As long as that leaving group's on a primary site, I would generally expect a Grignard to attack through an SN2 substitution, pushing out the leaving group to create a new carbon-carbon bond. So that should work. All of those efforts focused on converting this molecule into an electrophile and then having a Grignard attack it. But we can also get there through another route. So what if we try to make this into a Grignard and have it attack the other 3 carbons? And if I want to make this into a Grignard, I would start by one of these 2 options, because that would, the oxygen would either attack the phosphorus or pick up a proton, make it a good leaving group, and then a Br minus from one of these 2 would come in there and push that out. So I'd have a Br there. Then, if I use magnesium and ether, I can make that into a Grignard. So now I've got this as a nucleophile, right? So this is a slightly different approach where I'm converting carbon 1 into a nucleophilic site, and I want to attack carbon 7. So what am I going to add here? I want carbon 1 to attack carbon 7 and leave something there that can be eliminated to make this pi bond. So that would probably involve a carbonyl. So if I still want to install 4 more carbons, right? I've still only got 4 carbons. I need 4 more to get to a total of 8. So I'm going to add 4 more carbons. Carbon 1 still needs to connect with 7. So I'm going to make carbon 7 electrophilic. Now, if I put a Br here, because it's on a secondary carbon, it's going to be too much sterics for this to directly connect. Plus, I won't have anything left over on there to make the alkene with. I can't start with an alkene and have a leaving group, because the leaving group can't leave a vinyl site and it's too crowded for it to come in from the backside. I can't do substitution on a vinyl carbon. And so what I'm going to do is make this a carbonyl. That will be pulling electrons away enough to make this a nice partial positive. And the nucleophile can attack carbon-7 and push these electrons up. So 1, 2, 3, 4. Carbon-7 now, when electrons swing up, it still has a sigma bond to this oxygen. It still has carbon-8. And it still has 5 and 6. So we're getting close. So after I use magnesium and ether to make the Grignard, I would add this, which is called 2-butanol. We'll talk about naming carbonyls later in the semester. Once that attacks, I get this intermediate. I've got a negative charge here. So the next step would probably be to add a little H3O plus, just to pronate that. And now I want to eliminate that and make the alkene here between 7 and 8. So to do that, I would start by making it a much better leaving group. And then I would use a sterically bulky base to make sure it picks off the most available hydrogen on this least sterically hindered beta carbon, right? This carbon here and this carbon here are also beta, and they have hydrogens. And if hydrogen were picked off, I get the alkene in the wrong spot, either between 1 and 7 or 6 and 7. But those are a little bit more crowded because they're secondary sites. So I can pick off the primary carbon selectively if I use a tert-butyl base, tert-butoxide. It should go for the more available hydrogen because it's so sterically hindered it would create too much repulsion if it picked off any of the other hydrogens. That would push electrons in. This would already have been tosylated, so that would be a great leaving group, and that would make the alkene right where I need it, so the MCPBA could make that area into an epoxide. So a few different options there that you could have had for your quiz answer. Obviously, I'll check those over and give you some feedback. Any questions about that one? All right, so there's a fair amount there. Lots of bullet points for you to look over and review before next week's exams. Lots of practice. Please let me know if you have questions about any of that. And then last semester we talked about IR, mass spec, and NMR in chapters 15 and 16. So this semester we're obviously not going to go through those chapters again. We're going to jump from 14 right to 17, and we're going to be talking about pi bonds a lot and the molecular orbitals involved with pi bonds in more detail, and looking at some reactions that occur in chapter 17. So you want to read that section and prepare so you can also answer the quiz questions that are due on Monday of next week, day 10. All righty.